Okay, colored pens, and we have 2 review questions. We're starting a new chapter today, so I picked a couple review questions from chapters in the past. Let's see what we recall. Number 1, what did you get when you simplified that expression? Start with extol, Sebastian R, and then Chris.
Negative 125 a to the
Okay.
125 a to 6 power b to 12 powers over negative 1.
Okay. Chris? Okay, they all sounded similar, but each one was a bit different. Anyone have an answer that matches somebody's, or want to introduce a different answer? Stephanie, Danielle, and then Dalton?
Negative 125 a to the 5th power.
Okay. Okay, so that was what somebody said over here, and you said what he said, I think. Dalton? Okay, the correct answer is negative 125 a to the 6th b to the 12th. Now saying 125 a to the 6th b to the 12th over negative 1 is really the same thing. You just wrote it in a little bit of a strange way. So 125 divided by negative 1 is negative 125. So you can mark yours correct, but we usually don't write answers over negative 1. Okay? So we will go over that one in a moment. What about number 2, going way back to the end of chapter 3? Way back. Let's see who's able to work through that. Start with Kadir, back to Extol, and then Ziamar.
Z equals negative 3 over 2 x y.
Okay.
Z equals negative 3y over 2x.
Okay. What'd you get, Ziamar? Okay, so we got a lot of different answers. Anyone want to concur with somebody or introduce a new answer? The correct answer is Z equals 3y over x minus 3. Now, let me put your mind at ease, because number 2, I tricked you a little bit. Not in the sense that it was a tricky question, in the sense that you're actually not quite ready for that question. You are, but you've never seen anything like it before. In fact, you learned the skill that you need to do number 2 just in the last chapter. You were introduced to the idea way back at the end of chapter 3. But you will not have to be able to do questions like this until Algebra 2. But I am going to demonstrate how to do it. Then we're also going to talk quickly about number 1. So let me back up for a second. Give me a thumbs up if you did this for number 2. Good. Put your thumbs down. Excellent. So that's something that you should have been doing. However, you missed a detail. You can't solve for z and then have a z on the other side. That's not solved for z. If you're solving for z, z has to be completely by itself. So even though dividing both sides by x will get this z isolated, it doesn't take care of this z. So now I'm going to demonstrate. You do not have to copy, you do not need to write, you need to watch. Because I'm going to show you where the skill from last chapter is involved. To isolate z, you need all the z's on the same side. So Matthew, to get all the z's on the same side, you had to first do this. That will jump this term to the other side. Here's what we're left with. xz minus 3z equals 3y. Now it seems like we went backwards, because I'm telling you to isolate z, and it seems like I'm getting close to isolating y. But we're not going to work with this. We're working here. And now you should see something that happened with what I just did? Something that we saw very often in chapter 9. What happened on the left-hand side? Nobody sees it? Janae? Yeah, both of the z's are on the same side. Very good. Not only that, but what did we do in chapter 9 that was something really important and new that you were doing over and over and over again? Okay? Factoring. So this, what do we call that when we have the same thing show up in both places? What is that called? Edgar? Say it a little bit louder. That's called a common factor. And what are we allowed to do, Alexandra, with a common factor? Factor it out. She said that beautifully. So the z is going to come out here along with this one. So the z is on the outside. What is left over on the inside? What's left over? Kayla? Very good. The unhighlighted part is left over, x minus 3. Now look at what just happened. Two z's magically morphed into one. Two z's morphed into one. Now we can get z by itself by getting rid of the x minus 3. Divide by x minus 3, divide by x minus 3. That will disappear, and we get z equals 3y over x minus 3. Comments, questions, concerns? So again, you're not going to be required to do this year. 2 years from now, you will get very good at this in Algebra 2. Okay? Any comments, questions? All right, let's go to number 1. What did you address first in number 1? What did you address first, Sebastian?
Simplifying the 25.
Ah, very interesting. So you saw that the 25 and the negative 5 had common factor. Give me a thumbs up if you did this first. You applied the 3 there, and then you applied it there, and there. Give me a thumbs up if you did that. Good. Put your thumbs down. Good. That's something that you should have done. Unfortunately, in this case, that ends up being the very long way. But before I get away from that, when I do a to the 4th to the 3rd, what does that become? Everybody in the room should know, because it's Mr. Gallett's favorite property. What does it become when we do a to the 4th to the 3rd? That's what this line is right here. A to the 4th to the 3rd. What does that become? Huh? Okay, but I'm saying, what does it become? What's the result? A to the 12th. Because when it's power of a power, what do you do with the exponents? Power of a power, what do you do with the exponents? Chris? Multiply them. So all my students who got A to the 5th, B to the 7th, I don't think you were multiplying when you were supposed to. Power of a power, you multiply. However, I would not have taken that approach if you were thinking at a very high level. Then you would look inside the parentheses. As Sebastian just pointed out, the 25 and the negative 5. 25 divided by negative 5 is negative 5. What about a to the 4th divided by a to the 2nd? What do we get when we do a to the 4th divided by a to the 2nd? Valerie? A squared. You said that beautifully. Because this is really 4 a's, and that's really 2. For those of you who don't remember, that's really a times a times a times a over a times a, and that cancels that, and we're left with 2 on top. That's what we talked about in chapter 8. So this is a squared. And what about b to the 5th over b. What does that become? Caleb? Michaela? B to the fourth. Very good. So you get b to the fourth, and now we have to the third power. Now it's much more manageable. -5 to the third power. A to the second to the third power is a to the sixth, and b to the fourth to the third power is b to the 12th. And -5 to the third power is -125. Any comments, questions, concerns on number 1? Anything at all? Okay, draw a line across your paper. Today we're going to begin chapter 10, and I begin each new chapter with an overview. I do not want you to copy the overview. I want you to pay attention to the overview. I want you to digest all the major goals we are going to be embarking on. I do not want you to copy them. Trust me, there's going to be enough things to copy. You're going to need the hand strength. So, chapter 10. We got 4 big giant goals, and each goal has lots of little ones inside. All eyes should be up there. You read it to yourself, I'm going to read along. So, you're going to be learning how to simplify square roots and approximate them and evaluate them. You're going to learn how to simplify radicals. You're going to learn how to solve quadratic equations using 4 different methods, and you already know one of them. You did it in chapter 9. It's called factoring. You already have done it. And we're going to actually start the chapter with goal number 4, which is graphing a quadratic function. Now, I never understood why a quadratic was called a quadratic. A quadratic is an equation that has an x squared. What does the prefix quad mean? What does the prefix quad mean? Only a few people know quad. Matthew, what's quad? Quad means 4. So I never understood, why does quadratic mean x squared when it means 4? So I looked it up to find out why. Here is why. And those of you who are fortunate enough in high school to study Latin, great benefits to studying Latin. I never did, but if you do, it opens up the world of language to you tremendously. But a quadratic equation is called quadratic because it comes from the Latin word quadratus, which is Latin for square. The leading term in a quadratic is always squared. And if you think about it, quad makes sense because a square has 4 sides. Any questions so far? Here are examples of quadratic equations. You have already seen all of these. In fact, if I asked you to, you should be able to solve that right now. No, we're not going to, but I'm telling you that you've already been working with them. I did not call it quadratic. What did I call it? In chapter 9, I called it something different. It was a different fancy word. You might even remember at the beginning of chapter 9, I had the word all over the place. I kept using the word over and over again. And then all of a sudden someone at the end said, "What is that?" Because no one knew what I was talking about. Kadir? A polynomial. I introduced chapter 9 and I said, we're going to learn how to add polynomials and subtract polynomials and multiply polynomials. And you guys are all like, what's a polynomial? Well, those are all polynomials. But now we're looking at one specific type of polynomial called a quadratic. And a quadratic is always with an x squared. The x squared is the largest degree. Any questions about that? So today we are going to learn how to graph this. So there is a lot of work involved. Today is going to be very difficult for a number of reasons. 1, the content is challenging. 2, there's a lot. 3, there's some new terms that you're going to have to learn. One question is going to take us 15 minutes. That's difficult to get through. So I'm telling you now that you're going to feel antsy, you're going to feel tired, you're going to feel drawn out, your brain is going to be stretched. I understand. So all I'm asking you to do is stick with it, keep working hard. You may not understand everything today. You will understand a lot of it, but you may not understand everything. That's okay, because we're going to be seeing graphing again next time as well, and it will start to sink in. I have been doing this for a long time. I know what I'm talking about, and I know what I'm doing, so you're going to have to trust me, okay? So we're going to start out with some definitions of terminology that you need. You may use as many abbreviations as you would like. Now you are going to be doing some copying because you're going to need some things to refer back to. A quadratic function or a quadratic equation is one that can be written like this. Y equals ax squared plus bx plus c. But a cannot be 0. If a were to be 0, then this would disappear, and that would no longer be a quadratic, that would now be a linear equation. So for it to be quadratic, that has to be, a has to be a number other than 0. You've already heard the term, now you're getting the formal definition, and I've kept the definition very simple. It's a U-shaped graph. It will either be a U going up or a U going down, an upside down U. Now we're going to be introduced to a couple of terms that are parts of a parabola. Parts of a parabola. One part is the vertex, and that is either the lowest point if the parabola is going up, or it's the highest point if the parabola is opening down. You're going to see examples of both. The axis of symmetry. One interesting aspect of parabolas is that the right side is a mirror image of the left and vice versa. And all mirror images need a mirror in the middle. The mirror in the middle for a parabola is called the axis of symmetry. The axis of symmetry will pass through the vertex, no matter what. And it will divide the parabola into 2 symmetric mirror image parts. Now, the next 3 items you are not going to understand until we actually do it. But you're going to need the definitions written down because you're not going to remember them, and you're going to need to practice, and you're going to have to constantly be looking back. Trust me, I know what I'm talking about. Again, it's not going to make sense until I show you in about 10 minutes. But this is something you're going to need. We are going to be learning something called a vertical stretch. Now, you do not have to write this. You need to read this, and then just write the part after the comma. When we compare it with y equals x squared, y equals ax squared is a vertical stretch if a is greater than 1. So the most important part is this. A is greater than 1 is called a vertical stretch. It gets confusing because there's something else, and it's called a vertical shrink. And eventually, you will be quizzed and tested on it, and you will have to know the difference between a vertical stretch and a vertical shrink. But it's going to take you a few days for it to sink in. So you need it copied down. A vertical shrink is when A is between 0 and 1. One other detail that we're going to explore is called a reflection. And when we compare our graphs with y equals x squared, it will be a reflection if a is less than 0. Less than 0. Now, I said something over and over again. I said this one detail over and over again. When compared with y equals x squared, when compared with y equals x squared, when compared with y equals x squared. That is one of our goals today. We are going to be comparing graphs with this one graph, y equals x squared. This actually has a name. I do not want you to copy the next part. You'll understand why in a moment. This is called the parent quadratic function. It sounds very fancy, but it's actually very simple. I said do not copy this part. You'll understand why in a moment. There's infinite quadratic equations, infinite. But there is the most basic one. The most basic one is y equals x squared. And it is called the parent quadratic function. This is it, right here. This is a picture of it. It's graphed for you. It always looks the same. It's the exact same graph. Okay? So a couple of points I want you to see. Its vertex is at 0, 0. There's a point at negative 1, 1 and 1, 1. And then there's a point at 2, 4 and negative 2, 4. If you can remember those 5 points, you can draw the graph every time. In fact, you will remember those 5 points, and by this evening, you'll be able to graph the parent function over and over again, and it won't be a big deal at all. Okay? Now, rather than have you copy all of this and then draw a difficult picture, I decided to provide it for you. So if my students at the front will pass back that, and I would like you to staple this in right below your other definitions, you're going to need this to refer to. Now, while you're waiting for the stapler, you don't need to freak out. You don't need to have it sitting on your desk. Just hold it in a position somewhere nearby, and you'll get the stapler in the next 5 minutes or so, and then you'll staple it in an appropriate place. So, we have a lot of things going on today. We haven't even started doing anything yet. We haven't even done anything. We're going to be graphing quadratic functions. After we finish graphing them, we are going to compare our graphs with this graph, and we will learn how to determine whether it is a vertical stretch, a vertical shrink, a reflection, and then there's one other detail. We're also going to talk about domain and range. So there is a lot. I already warned you ahead of time. I'm just going to reiterate my warning. You're going to be tired. You're going to be frustrated. You're going to be antsy. You're going to be ready to just give up. Don't. Trust me, you will be okay. Okay? Anyone have any comments or questions? Good. So now we're going to actually do something. Do not start copying example 1. I put big red letters. What did I write in big red letters? This is from what? Nathaniel? Yeah, this is actually from the next lesson. I could have skipped over 10.1 with you guys, but then it would have been so ridiculously challenging, and it would have made no sense to anybody, and I would have had to go backwards anyway. But I wanted to show you what our real goal is. We are going to do this question tomorrow. You're going to learn how to graph this tomorrow. But if I started with this, it would become extremely difficult. So here's what we are going to do. Today we're going to learn how to graph quadratics that do not have a middle term. If you take out the middle term, everything becomes much easier. It's not going to be easy, but it's easier than it was when I had. This is easier than that. Okay? So this one change makes a huge difference. So we are going to start with this one. So now you can go ahead and write example 1. Do not copy the instructions. You're going to read the instructions. I write the instructions here the same way they're phrased in the textbook and the workbook and on tests and quizzes so that you can see what it's going to say and what you're supposed to do. So, graph the function. Identify its domain and range, and then compare with the parent function. So here's what we're going to do. We are going to learn how to graph this. We're going to do something with this. We're going to graph here. Then, after that, we're going to do domain and range. After we establish the domain and range, we're going to do what's called the comparison, where we compare our graph with the graph of the parent function. So we're going to have things written here. We're going to have a whole graph. We're going to have a domain and range and a comparison. Not easy. And it's time consuming. As I said, each question is going to take 10 to 15 minutes. So now, we're not going to worry about the rest. We're going to focus. If everyone will turn to the back of the room and look at chapter 4. You learned how to graph a linear equation using slope-intercept form. You learn how to graph a linear equation using intercepts. But there was a method you learned before you learned that and before you learned that. What was the method you learned before this and that? John? Yeah. Table of values. I even have an example up here. It's probably hard for you to see if you're way up there, but you see that we picked x values, we plugged it in, got y values, plotted the points, and drew a line. At this point, that should seem pretty easy. I mean, just thinking about it, you should be like, yeah, that's no big deal. -2, 3, plug it in, boom, draw a line. Well, guess what? That's the exact same thing we're going to do. We're going to make a table of values. The only difference is that we have to be a little bit more conscious of the numbers we choose, and the drawing that we make is a little harder to draw because it's not a straight line. drawing a curve is harder than drawing a straight line. So, the table. First of all, when there's no middle term, the vertex will always be 0, something. That reason alone makes this one much easier than the other question I showed you. So we can already fill in our table with 0, something. Now, how do we get the y value that goes with the 0?
Plug the 0 into x.
That's right. Plug the 0 in for x and simplify. 0 squared is 0. 1/3 times 0 is 0. Plus 2.
2.
We get 2. No big deal. So we already know that 1 point is 0, 2. No big deal. Now, when we did linear equations, usually what I told you to do was just use 0, 1, and 2. And we can do that. However, we need to think about some things. When there is a fraction in the function, that will make our numbers come out very ugly, very unfriendly. And since we have to graph this on a grid, I don't want to have to graph thirds or ninths. I mean, how do you graph 2/3 in here? Is that going to be very accurate? It's not going to come out very nice. So we don't want to deal with the thirds. So we can actually be very creative about what numbers we choose here and here to make this come out really nice. What number could we choose? Let's just start with this one right here. What could I choose to go right there to make it really nice? Michaela?
3.
Yeah, if we choose a 3, and this is something we've done before, if we choose a 3, watch what happens. So let's put a 3 right here, and then we're going to do what Dave instructed us to do. Put the 3 right here. 3 squared is 9. 1/3 times 9, what does that come out to? 1/3 times 9? Everyone in here should have instantly known. Alexandra? 3. 3 plus 2 is 5. So we already know that the next point is 3, 5. Thinking about logic, what should we use next? What would be the next best choice? 6. Let's see what happens. Plug in a 6. 6 squared is 36. 36 times 1/3. What do we get for that, Edgar? 12 plus 2 is 14. We got a nice, friendly number. Okay. The other one? Okay, so we'll see if you got it. But does anyone have any questions for these? And again, we chose these because of this fraction. If the fraction wasn't there, we could just use 1 and 2. That's fine. Okay? All right, Michaela, let's go to the other side. What do you think we should use right here? Very good. We want to make a mirror. This is the mirror right here. So we don't want to make a mirror. We want a mirror image. This is the mirror right here. And so we want to go the same distance to the left that we went to the right. So in other words, we went 3 and then another 3, which means we want to go 3 in this direction and then another 3 there. That will make a perfect mirror image. Watch how this is a huge benefit. If we put a -3 right here, we don't have to do anything. The y value will become the same y value as this. That's the power of the x squared. A -3 and a +3 both have the same square. What's -3 squared? Chris? +9. What's +3 squared? +9. So even though this is a negative number, watch what happens. Negative 3 squared is 9. 9 times 1/3 is 3. 3 plus 2 is 5. But we didn't have to do it because we already knew it was going to come out to 5. Negative 6, what will the y value be for negative 6? John? Positive 14. The y values will mirror. Now, a common mistake is students will say, oh, well, this is positive 3, positive 5, that must be negative 3, negative 5. But that's not what happens. The x values are opposites, the y values are mirrored. Okay, you're going to see why in a moment. Does anyone have any questions about the table? Good, so let's go ahead and now graph. We need to fit on our graph all the way up to 14. So I got to be careful, I got to make sure I have enough space to do that. 1, 2, 3, 4, 5, 6, 13, 14. So I'm going to put my horizontal axis way down here. Now you have graph paper, so it doesn't really matter as much because your graph paper continues on up and to the right and down. My graph paper ends here, so I have to be careful about where I put things. So I'm going to put my x-axis down a little bit. My y-axis doesn't matter, so I'm going to put that right in the middle. Hopefully that's the middle. Is that the middle? And now we're going to plot the points. Nathaniel?
Can we substitute the graph for, say, linear for 10? So that's 2, 4, 6, 8, 7, 8.
Yeah, you could go by twos, as long as you go by twos in both directions, sure. So, 0, 2, that's going to be right there. 3, 5. 1, 2, 3, 1, 2, 3, 4, 5. That's the point right there. 6, 14. Well, here's 3, 4, 5, 6. Now I got to go up to 14. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. I counted perfectly. Here's why it mirrors. Here's why the numbers mirror, because now I want the same point but on the other side. So I want that point right there so I can draw the parabola. If it was negative 5, then this point would be all the way down here and it wouldn't draw a parabola. And now I want this point but on the opposite side, so I'm going to go 1, 2, 3, 4, 5, 6. And now I have that point there. Does anyone have any questions on how we plotted those points? Guys are doing a good job. I'm telling you, it's a long process. It'll get faster and faster as we get better and better. Remember, this is the first time. Any questions so far? Now we're going to attempt to draw a smooth curve. It's not easy. It's going to take you time. You're probably going to mess it up. Draw your curves lightly so you can erase it if you need to. It's not a triangle. It's a curve. So we're going to draw a curve from here, and it's curving up. And I might have to redraw it myself. We'll see how I did. I did okay. And then it's going to curve the other direction. And that is a parabola. Good. So we've drawn a parabola. Now we have two jobs to do from there. We need to identify the domain and range. Now, the domain and range do not come from the table because the table came from our brain. The domain and range is going to be true for the whole parabola. So you have to say to yourself, well, could we have chosen positive 1? Yeah, we could have used 1, we could have used 2, we could use 12, we could use 50. We could keep going all the way to the right for the x's. And we could keep going all the way to the left. So our x values could be anything. And the way we write that is by writing all real numbers. The good news is that pretty much every single one that we do today and tomorrow is going to say all real numbers for the domain. The only exception is when we do real-world scenarios, and you'll see one at the end of today's lesson. The range is the hard part. But it's not really hard. It's just something that you actually have to think about for a moment. The range is all the y values. So what y values are being used? So let me show you what I mean. I'm going to draw a horizontal line right here. So that's the y value of -2. Right now that's on -2. Is -2 on the graph anywhere? No. So -2 is not part of the range. What if I move this here? Is that part of the range? No, it's not on the graph anywhere. What is the first point that is on the graph? Dalton? 2. So the 2 is the minimum. From there, all of these y values are used. So every number above 2, every number up here is used. It's the numbers below 2 that are not. So here's how we write a range. We say the y's are greater than or equal to 2. Take a deep breath. Because now we got the last part, our comparison. Now, for the first couple of times, we're going to draw it out. After the first couple of times, you don't have to draw it out anymore, and you'll see why in a little while. But now to do our comparison, we need another graph on our paper. We don't need a table for it. We already know what it's going to be. It's going to be 0, 0, 1, 1, -1, 1, 2, 4, -2, 4. This is called the parent function, so you have to draw this out. This is the parent. We are comparing to y equals x squared, and I'm drawing y equals x squared in green. And so now I'm going to sketch this. And now we're saying to ourselves, how do we get the purple one? To you it might look blue, bluish purple. How do we get the purple one from the green? So if I start from the green, what would I have to do? I would have to push the green edges out a little bit, and then I would have to move the vertex up a little bit, right? So if I take this graph and move it up, and push these out, then I would turn into the purple. But there's a technical way to say that. This is called a vertical shrink, and you could put vert shrink. It's a vertical shrink because we are using a fraction right here. And when you multiply anything times a fraction, the number gets smaller. So this is called a vertical shrink by a factor of 1/3. I got that from the actual function. That number, this number right here, tells us how much we shrink it by. And we know it's a shrink because it's a fraction. If this was a whole number, like a 2 or a 10, that would be a stretch. The second part is how do we get this to move up? That's called a translation. We translate the vertex up 2 units. So this is a translation 2 units up. Again, the point of the comparison is to be able to look at this graph and get the other graph from it. So if I vertically shrink the green one by 1/3 and translate it 2 units up, I end up with the purple one. Now, you may have questions, you may have no idea what's going on. You're probably copying feverishly and you're trying to get it, and I understand that. It's going to take some time. We're going to do another one that's going to go a bit faster. Going to go quite a bit faster. I did tell you it would take 10 to 15 minutes, and I think that took about 15 minutes. Any questions, comments so far? Dalton?
The translation is for basically the range.
Well, yeah, but look at the... Anyone see the translation up in the function? 2 units up, and there's a 2 right there. And that also tells you this number right here. So there's a connection between this, this, and this. Janae? Any comments, questions? All right. So now let's look at a different one. Example 2. Read the instructions, but you don't have to actually copy them, and then copy the function y equals negative 3x squared. So now we have seen the process, now we can move much faster. Table of values. We already know the middle, the vertex is going to be 0 comma something. Plug in the 0. What do we get out? One way to keep yourself alert and involved is to participate, get yourself involved. Nathaniel?
Yeah.
We get a 0, very good. So the vertex is 0 comma 0. What numbers should we put here and here? Can someone help us choose these 2 values? Let me highlight it so you see what I'm talking about. Someone help us choose these 2 values. What should we put? Got 4 people who have an idea? Stephanie? Yeah. Keep it simple. The only time you need to pick something different is if that's a fraction. In this case, 1 and 2 works very well. Plug in a 1, do mental math. 1 squared is 1 times negative 3, negative 3. Plug in a 2. 2 squared is 4. 4 times negative 3, negative 12. Any questions on how we got those numbers? Now let's go to the other side. What should we put here and here? Caleb? Negative 1, negative 2. We want to mirror. What will this value be? Kadir? Negative 3, it will be the exact as this. What will this value be? Edgar? Negative 12, it will mirror this. Anyone already know something about this graph that's different than the one we did? Davis?
It's gonna be an N.
Okay, good. Dalton? And then Kadir?
And the other one is you said that there's a transition, right? The last number is
Very good. Excellent observation. That's right. That's what he was saying, was the vertex is going to be the same as the y equals x squared. Absolutely. Very good. So let's go ahead and graph this. And now I need to make sure I reach negative 12. So this time I need to put my x-axis a little bit higher up. So I'm going to make sure I do that. I'll put this way up. Let's see if this is good enough. Up there. And plot the points and draw a curve. 0, 0. 1, negative 3. 1, 2, 3. Negative 1, negative 3. Positive 2, negative 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then there's going to be one on the other side. Remember, it's not a triangle, it is a curve. So you got to have an element of curve in there. And so here's the curve. And mine's far from perfect. Yours will be far from perfect. You continue to do the best that you can. If it's really awful, erase it and try again. I would say mine's not great. It's kind of bad, but not so awful that I would erase it. So does anyone have any questions on how we got from the function to the table or from the table to the graph? So, domain and range. It's going much faster now. I mean, the last one took 15 minutes. We're not even at 5 minutes yet. We're just barely at 5 minutes. Domain. What's the domain? John? It's all real numbers because the x's could be anything. But the range is a little bit harder. I'll give you a hint. It's going to be y and then some symbol and then a number. So what should it say? Got 3 people who have an idea. A lot of people still drawing. Michaela? Very good. We're going to say less than or equal to 0 because 0 is included in it. But yeah, you got the basic idea. And then our comparison. We need the parent function on our graph, and it's easy to draw. The vertex is at 0, 0, so I'm just going to put another dot right there, and then we go to 1, 1, negative 1, 1, 2, 4, negative 2, 4. It's the same every time. And now I'm going to sketch the curve. And now compare. Davis already pointed out the first detail. He said it was an N instead of a U. Well, that's not what we say. We call it a reflection. You know it's a reflection already because of this right here. If that's negative, then it's going to be a reflection. So the first detail is it's a reflection. Now, there's a number right here. That number tells us whether it's a vertical stretch or a vertical shrink. Which one is it? Vertical stretch or vertical shrink? You probably have to look back to see. John? It's a vertical stretch. The number's going to get bigger, so it's a vertical stretch by a factor of 3. We don't include the negative sign because the negative sign told us it's a reflection. The whole number tells us it's a vertical stretch. There's no translation because of what Dalton explained and Kadir pointed out. The vertex is the same vertex. We didn't translate it up or down, so we don't have that detail. You would have also seen something here. +4 or something like that would mean we're going to translate up or down. Since there's no C value, there's no number here, then there's no translation. Every number in the quadratic tells us something about the graph. So, comments, questions about this one? So, example, yes, Daniela. This number right here. Whatever number is right there is the factor. The negative sign tells us the reflection. So the negative sign is not part of the factor, just the number. Okay? Good, very good question. So we just cut the work time in half. From example 1 to example 2, we already cut the time in half. Now you're going to do a third one on your own. It's going to take less time than that. Okay? So, checkpoint number 1. Graph the function, identify its domain and range, and do a comparison. You got 6 minutes. Take a few seconds to finish up, and then I will reveal. Now, the picture I'm going to reveal doesn't look as good as most of yours. The computer program I used didn't draw it as long as yours did. So just trust me, yours is probably correct. I've already walked around and looked at most of yours. So this is what the graph looks like. So I want you to focus on a couple of things. You should have the vertex at +3. You can see that right there, that's going to be at +3. And then you see these points right here at -1, -1, and +1, -1. Okay? And then I think it goes all the way down to 2, -13, and -2, -13. So I couldn't get the computer I could have gotten the computer program to draw it for me, but it would have been so tiny that you wouldn't have been able to see it. So I chose to blow up this part of the graph so it would be easier to see. Okay? Here's the domain, range, and the comparison. And the table that I used. The domain is all real numbers. The range is y is less than or equal to 3. I think we're getting used to that. That's not that hard. The comparison takes a little bit of effort. It's a reflection, because it's upside down. It's a translation 3 units up, because we had to translate the vertex from here up to here. And then it's a vertical stretch by a factor of 4, because there's a 4 right here. Comments, questions, concerns? Give me a thumbs up if you got at least part of it correct. Okay, think about what I just asked you, because that was important. Good, put your thumbs down. That's my expectation. I told you at the beginning, you're not going to get everything. It's too much. But I have to do it all today, because we've got so much more coming behind it. We needed to get it out of the way. So you guys are doing a very good job. Keep it up. You're going to breathe a sigh of relief when I show you the next thing we're going to do, because it's not going to be drawing a graph. But you have to pay attention to what we just learned here and what each piece of this means. This has meaning, this has meaning, and this has meaning. What does the negative tell us? What does the negative tell us? Danielle? That it's going to be upside down. So if it's positive, it opens up. If it's negative, it opens down and is a reflection. Excellent. What about the number next to the x squared? The number itself tells us what? Chris? Very good. That will tell us vertical stretch or vertical shrink and the factor by which it will be. What about the last number, the c value, the constant? What will that tell us? Anyone figure that out? John? That's right. It also tells you, you're absolutely right, that's a translation of how many units up or down. It also tells us something else. What else does it tell us? Kadir? Well, the curve is all, the whole thing is a curve. Yeah, the vertex. It tells us exactly where the vertex is going to be. So, both are important. What John said was very important. What Kadir is saying is important. This number tells us where the vertex is, which also tells us that we have to translate from here up 3 units. Very good. So watch this. Example 3 is about using those pieces of information in your mind. So, example 3, different instructions. Describe how you could use the graph of y equals x squared to graph these. So, in other words, if I had y equals x squared, what would I have to do to it to turn it into y equals x squared plus 6? So I can do things like I could move it up or down, I could shrink it in or out, or I could reflect it. So if I have, let me see if I can, if I have the graph, what would I have to do to it to get this picture? Ziomara, what would I have to do? Move it up 6 units. How did you know that? That's right. All you would have to do is move it up 6 units because that's the only detail there. The coefficient here is positive and it's a 1, so there's nothing different about that. The only thing different is the plus 6. So here we would have to translate up 6 units. The point here is that you should be able to look at this and already know in your mind approximately what the graph is going to look like. You already know it's going to be the same thing as y equals x squared, except it's going to be up 6 units. What about part B? If I had the graph of y equals x squared, what would I have to do to this graph to turn it into this graph? So give me one thing that I would have to do. Chris and then Danielle. I would have to reflect it. This negative sign right here says reflection. So let me just move this out of the way. So I would have to reflect. What else would I have to do? Danielle? Translate down. Beautifully said. Translate down. 7 units because it says -7. Right here. What else? Michaela? Very close. Very good. We're going to do vertical something. Which one are we going to do? A shrink or a stretch? Alexandra? It's a shrink because it's a fraction. So yeah, you were right there. You just got to get the right word. It's a vertical shrink. A fraction will shrink things down. A whole number will make things grow. A vertical shrink, and she already said by a factor of 1/2. If we do those 3 things to the parent function, it will turn into this. Okay? Those 3 details. Positive or negative, fraction or whole number, number over here. Those 3 details tell us what's going to happen. Does anyone have any questions about that? John?
If you do this on a graph, you would get the graph using table.
Yep. So if you are able to do that, the only hard part is the vertical shrink by 1/2. That is, I can't explain how to do that. It's way too complicated. But if I gave you this, if you had to graph that, yeah, you don't have to do a table. You could actually draw y equals x squared and then just move it up. So that's an awesome idea, John. That's a high-level connection that he just made. Very good. Any other comments, questions? So now I'm going to give you a checkpoint. It's related to this, a little bit harder. It's designed to make you think. So it might take you a moment to digest and think about it. But it's really not super challenging. It's just a little bit different. How could you obtain the graph of G from the graph of F? Take 2 minutes to describe how you could get G from F. how would you get G from F? 1, 2, 3, 4, 5, 6, 7. Good. We'll start here and go right around. Chris. Okay. What did you think?
You'll do the F graph, then bring the vertex down by 5.
And that's what you said move it down 5? Okay, and you say move it down 5, so draw it. Okay. Here, 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 and here. What did you think?
Grab the F and then move it down 5.
Okay, so that's pretty similar to what they said. Nathaniel? You translate down. Good. Okay. Michaela? Oh, so we seem to all agree that it's just translated down 5 units. That's exactly right. I'm actually incredibly impressed because the idea was to notice that everything else about the graph was exactly the same, so the only difference is that this one was down 5 units from that one. Outstanding work. Give me a thumbs up if you were able to figure that out. Wow, I'm very impressed. Outstanding. Amazing. Beautiful work. Okay? Put your thumbs down. So we're going to wrap up with the real world example of this, and I've been using the same model for a while now, the vertical motion model, but this is a slight modification of that which we were introduced to, which is not vertical motion, it's a dropped object. You do not need to copy the question today. I don't need you to copy that, but you do need the function. H equals negative 16t squared plus 20, and this is what's happening. Foam ball, and this is actually a foam ball, and it's being dropped. So we went through this. We talked about examples where throwing it, and I am adding a force by throwing it across the room, and I am adding muscle force that changes the way it goes. But this is different. The only force affecting it is what? Gravity. And that's accounted for here. The negative 16 is the gravity. So the only thing we never saw with vertical motion was the graph of it. And so what does the graph of it look like? Well, I've already set up the graph for you. So you're going to use this exact graph. And I've already set up the table for us. So we just need to fill in the table. What numbers do you think we should use for here and here? What should we use? One person has an idea, 2 people have an idea, 3 people. What did you think, Chris? Yeah, I actually tried to make it super easy for you. I already put even though this is t, it's the x values, but we're using the letter t to represent it. And so I already put them on the graph, so you can already see that that's what's going to go right here. 0.4 and 0.8. And now plug things in and work it out. So let's do the 0. That's easy. Plug in a 0 right here. That will become 0, and that's a 20. So 0, 20. 0.4 is a little bit harder, and we're probably going to need a calculator to work through that. We have to plug in a 0.4 here, square it, multiply by negative 16, and then add 20. But if you do it in the right order, you could just use your calculator to do the whole thing. 0.4 times 0.4, that's squaring it, equals times negative 16. Well, I don't need the negative. I can just do times 16. And now flip it to negative. And now add 20 plus 20. 17.44. So this comes out to 17.44. Same thing with the 0.8. 0.8 times 0.8 times negative 16 plus 20, 9.76. 9.76. What about the other side? What should I put here? What should go here and here? Nathaniel? Negative 0.4? Like this? Okay? And then negative 0.8? Okay? Anyone have a comment? One person has a comment? I think I've destroyed the functioning of your brain over the course of the day. Davis?
I'm not sure if you're allowed to put negative numbers for motion.
Why not?
Because there's no such thing as a negative time.
So you said you weren't sure, but actually you were quite sure.
That's what I said. I just meant.
Yeah, he's quite sure. Yeah, there's no such thing as negative time. So in fact, we cannot put negative 0.4 and negative 0.8. And in fact, I tried to trick you a little bit, but we will not use this side of the table. In fact, if you look at the graph, this is only the first quadrant, so it won't go to the other side. So now we can plot the points, and you are going to have to estimate a little bit. 0, 20, that's the vertex. 0.4, 17.44. Well, there's 16. 18 is going to be halfway, so a little bit less than that. That's going to be 17.44. And then 0.8, 9.76. Well, there's 8. 10 is in the middle, so I'd say just slightly below where the 10 would be. That's going to be about 9.76. And now try to draw a curve. And so this is how the speed with which the ball will drop and where it is at each point in time. Now, I apologize for this, but I'm way over, I'm over schedule, so I'm going to quickly go to your homework. Okay? So, draw a line across your paper. Your homework is page 652, numbers 4 through 36 even, 42 and 46, but hold on, because I'd like to change that. So I'd like you to start not on number 4, start on number 14. So number 14 through 36 even, and I think that takes off 4, 6, 8, 10, 12. That takes off 5 questions, so that will be 14 questions instead. So please change that to a 14. Make sure you read the next section. That will help you a lot.